start up here in a couple minutes. Appreciate your patience. Yeah, thank you for starting the recording. I appreciate that. Okay, maybe we get started. Hello, everybody. My name is Peter Christensen. I'm a project manager at Pacific Northwest Natural Laboratories. I will be moderating today's session again, and I'll introduce Alex here, and I'll just as a pre-note, what usually works best, since we have both online and in-person people at the room there, is to hold off questions until the end. Most likely some of your questions will be answered later on in the presentation. But just so that to keep the continuity, I appreciate if we could hold all of our questions to the end, and we'll be able to take questions both online and from the room. So it is my pleasure today to introduce Dr. Alex Anderson. He is a power systems engineer at PNNL. I think he's been here for about 5 years now, almost. And he is in our systems engineering group. He is has a master's degree from WSU, go Cougs. He has a doctorate degree from Colorado State University, and I can tell you it's been my personal pleasure to work with Alex over the last year or so on a project, and I can tell you guys are in for a great treat today. He's a great presenter. So Alex, take it away. Thank you.
Thank you, Peter. I'm going to be talking today about some of the emerging challenges in the data integration space and how do we exchange data across the transmission distribution boundary. I'm going to start off by giving a little bit of context of why that matters, what data integration is, and then some of the resources and new approaches that we have been developing to solve that problem, working with our utility partners in Vermont. I'm going to start off by talking about some of the silos of the electric grid. This is a lot of background material, and so I'm going to be going through it relatively quickly. First off, we start with our basic divisions of the electric grid: generation, transmission, distribution. We talk about it all day. When we start looking into some of the specifics, we see differences in the representations and then also in the types of measurement data and observability, where in transmission, it's one large centralized three-phase balanced model with high observability. In distribution, we have thousands of independent single-phase, two-phase, three-phase feeders with very little measurement data coming in through traditional means and very rapid system changes that are only becoming more rapid through decarbonization and the proliferation of grid edge technologies. Next, we have silos of functional entities. This is a grid architecture representation showing the different stakeholders within the electric grid. where we have generation owners and operators, multiple operating entities within transmission, more and more operating entities within distribution, and very complex interactions between these entities, but each of them have their own representation of the system and their own data silos. The software systems used by these entities are also siloed generally, with a very limited amount of information exchange through Intercontrol Center Communications Protocol, or ICCP. Each software package has their own representation of their portion of the electric grid and their own set of applications and services that are used to perform analyses and grid control. When we dive into a single entity, a single transmission operator, or a single balancing authority, or a single distribution provider, we find data silos between the departments of a single utility. And so the operations department will have a SCADA node breaker type model heavily focused around the real-time position of breakers, transformer taps, megawatt, megavar measurements. The planning department will use an entirely different model in Power World or PSSE, or on the distribution side, SIME Synergy, looking 5 years out, 10 years out. GIS will have an entirely different set of information and is often the system of record for distribution utilities, and everything is just points and polygons. There's no physical representation of electrical connectivity. Then customer billing, asset management, and then the catch-all that if it doesn't fit into those 5 silos, we put it in an Excel spreadsheet. We have lots and lots of Excel spreadsheets across the power system industry. And so previously, without a lot of grid edge, distributed energy resources, we could manage. It was ugly, but we were able to get things done, and we were able to keep a resilient, reliable, secure electric grid. Now with these technologies, we're also facing silos in technical expertise, where individual people within the same utility also have their own siloed views of the world, where you take an operator, an engineer, an application developer, and a cybersecurity defender. They are not going to use the same words to mean the same things. And we need some sort of a structure to bring everybody onto the same page, to be able to exchange data between these different entities and be able to tackle the challenges that are facing the grid. Finally, the last silo, when we start looking at representations of even the same piece of equipment, we find different representations, different names, different parameters stored in between different representations. And so this really brings why we need the concept of information modeling. What information modeling refers to is being able to provide a common environment so that we're able to ingest models, measurements, data streams in a consistent format, have a consistent identifier across those different data streams, be able to associate time series measurement data with the correct physical asset, with the correct electrical network mathematical model. And we need to be able to share that data in a manner that is understandable to all compatible applications that speak that data model. And that is what we refer to by an information model. It's a consensus-based vocabulary that is agreed upon by an industry and in a sufficiently large user base so that we can define objects in a consistent manner. We can also say a model is canonical if it covers the entire canon of the electric grid, so that It covers the different use cases of asset management, operations, planning, and so on. And most importantly, it needs to be able to identify information with specific enough detail and enough context, metadata around the data, so that we know exactly what we're referring to. If we just take an arbitrary data string, 76, 47, 14, 5, that could mean anything, really. It could be substation 76, 47, bay 14, breaker 5. That makes sense. It could be a very weird calendar date, or it could be the chemical abstract identifier for table salt. Without the metadata, without the context to understand that string, we have no idea what that data is actually telling us. This is where ontologies come in, and we have the difference between syntax in a communications protocol and semantics in providing the metadata around what we got in that communications message. A syntactically correct statement, it's like your messaging structure. Did you format it correctly in DNP3s, IEC 61850, whatever? And you can put any garbage you want into that message and send it by DNP3. And an example I like to make is the sentence, my transformer has a green shirt. It has a subject, it has a verb, it has an object, it has a period. From a syntax standpoint, this is a completely valid message. The message itself, though, is garbage. It has no meaning. And what semantic models do, what information models do, is provide the structure so that what we are saying actually has meaning. And so a semantically correct statement would say transformer tank number 50 has a high side voltage rating of 4 kV. And we cannot specify anything else that is not allowed by that ontology. In the power grid domain, that ontology is the common information model. It gives us a fully standardized way of representing data, exchanging data between different vendor systems, and in this context, most importantly, it is the only consistent representation of power systems equipment across the generation, transmission, and distribution boundaries. We are beginning to move into the customer side, but that data model is not fully mature yet. It is published under an Apache 2.0 license, so it is free to the world. It's not exactly the same thing as public domain, but an Apache license is similarly permissive. You do not need to purchase the IEC standards to use SIM. The IEC standards go and provide additional documentation, hand-curated diagrams, that type of business use cases on top of the information model, but they are separate. In the transmission distribution modeling context, SIM gives us the ability to combine transmission and distribution models into the same data model, into the same database, and use the same classes and attributes. And so here we have a high voltage transmission line, 115, 230 kV, whatever. It's an AC line segment. Here we have an underground distribution cable at the 12 kV, 13 kV level. It's an AC line segment. Here we have the secondary triplex line from the pole top transformer to the customer meter. It's an AC line segment. They all have the same attributes. They all live in the same database. You use the same query to get all three. And you don't have that disparate modeling problem of what would happen if you were to try to combine, say, PSSE with OpenDSS. They have vastly different representations and views of the world. And the only thing you have to get right is just the boundary mapping, because you need to make sure that you have consistent identifiers on either side of the feeder breaker. In a utility context, this is really important, because this allows us to move towards a single source of truth. We can create that combined transmission distribution model and populate it with equipment, topology, SCADA points, AMI points, Internet of Things, data streams. and avoid duplication of models and interfaces. Now, what is important to remember is SIM is not the end-all solution. It's not a technology solution or a software. It's not a database. It's not a communications protocol. It's how you format that data once you get it back so that you're able to understand the context of that data. It lives just at one level of a much bigger standards and protocol landscape. And so here on the left, we have the traditional OSI stack for TCP/IP type information exchange, and the GWAC stack for representation of utility business functions. And SIM lives up here, the semantic understanding and the business context and procedures at the application layer. You still need your presentation, session, transport, physical, all of those additional layers and all of those additional protocols to get full network interoperability. And then you also still need your regulatory and policy standards like 1547, California Rule 21 for inverter performance, 2800 for large-scale IBRs. You do need that full standards landscape, and you do need to choose what best works for your individual purpose. Each of the protocols, like, okay, we're going to do 1815 for the DERs, and then you have multiple choices of your communications protocol, multiple choices of the physical layer, multiple choices going top to bottom. But SIM provides that context, which is really key. Now let's talk about what we mean by data integration. Data integration is about providing that single source of truth of your modeling data, your time series data, metadata, in a manner that you can get it in one place, but it also has all the correct associations. And we need to be able to combine a mix of existing data streams, SCADA, field telemetry, large DERs that are metered directly by the utility. Existing data that the utility is bringing back, but is not aggregating in real time across almost every single distribution utility. They're bringing back AMI smart meter data every 15 minutes, every hour, but they don't aggregate it until the next business day. So we have perfect visibility of what happened yesterday, but we don't know what's happening right now. And then emerging data streams from IoT devices, smart inverters, micro PMUs, emerging point-on-wave data. We need a way to bring that back together, map it to the correct physical asset, map it back to the correct modeling object in your PSSE or OpenDSS simulation. And with that comes three different approaches to doing data integration. The first is you go to your favorite vendor and you buy a top-to-bottom EMS, ADMS proprietary solution from GE, Siemens, AspenTech, your favorite software provider. And they're going to use their own proprietary databases, data stacks, API, applications, and it works top to bottom. And that works reasonably well if you're a vertically integrated utility. As soon as you need to exchange data with another utility that's not using the same vendor, now you get into the second paradigm, which is custom application-to-application adapters. And these are hand-built. You bring in a consultant, they're going to do these data mappings. They're very fragile, they're costly to build and maintain. And every time you need to do a new exchange, you need a new adapter. Quickly, it becomes unmanageable. And that moves us to the third paradigm, which is a agreed-upon information model providing the single source of truth for a standards-based platform. Now, the applications, instead of communicating with each other and direct application to database connections, they all talk through an enterprise message bus. It's a many-to-one communication paradigm where they all communicate on the message bus. They have their topics, they have their information that they share, and we only have to build one interface from the application to the platform rather than many-to-many. The Common Information Model under IEC Standard 61968-1 defines how that enterprise service bus should be created, the business use cases, and how you set up a data-rich environment. And that message bus allows us to map different types of data. We have our time series data like SCADA, AMI, weather, load messages. We have our network models. We have our applications. We have shared services like topology processor, power flow, Y-bus, and they all communicate across the same shared message bus. All of the queries for information are passed through the message bus, and all outgoing control commands. So if I want to send a DNP3 message or an IEEE 2030.5 control message to DERs as an application, I publish that onto the message bus, and then the correct device protocol converter will get it out to the field. An example of a reference implementation of this service bus protocol and open platform is GridAPPS-D. GridAPPS-D is a platform built by PNNL with a lot of involvement from WSU and our industry advisory board, where we have created a reference implementation of that architecture, Python and Java libraries for doing the API calls, and a development environment to build applications that are compliant against the Common Information Model. A view that I like more than the software architecture diagram is it's a data pipe. We have all of these disparate data sources coming in. We can put them through a pipe. They all get combined together, and now at the outlet of that pipe, your application can make controls, intelligent decisions, training data, and you don't have to do all of the piecemeal combinatorial data-to-data mapping. GridAPPS-D as a research platform also provides a robust development environment in Python where you can build very quickly applications in Jupyter notebooks, interface them to a simulation in GridLab-D. We're currently working on adding PSSE, OpenDSS, other solvers to that environment. And you can see here is a very simple application. It's just opening and closing a switch on the feeder, and you can see each time that Python block runs, it's showing up in the visualization and also the time series strip charts included by GridAPPS-D. Now let's talk about distributed architecture. We've talked, everything we have done up to this point is what we would call centralized. We have one database, we have one message bus, we have one single source of truth. And as we start seeing more and more grid edge devices, more and more smart homes, virtual power plants, microgrids, trying to do everything in one location is going to break down. It's very hard to get that much information through a single pipe. And so this is where the concepts of distributed architecture come in. And this work was largely led by Dr. Dubé, working with our PNNL team, creating that initial concept. And then we're going to show how we have reduced that to practice with some of our utility partners in Vermont. So we have that concept of the enterprise message bus where all of the data is going through. Now let's make that distributed. So instead of one message bus for the entire utility, let's do one for each subtransmission area, one for each substation, one for each feeder, one for each microgrid within each feeder, one for each cluster of smart homes that might be participating in some kind of demand response program. Now we have made the data problem that much more manageable by compartmentalizing the data and making it available just to the consumers who need it. Does the substation controller really care about the individual messages between different components within the microgrid? No, it just cares about the total P and Q and what impact it's having on the overall transmission system and equipment within the substation. So by doing that data compartmentalization, you make the problem significantly easier. Distributed is a very broad word. It can mean a number of different things. It can be hierarchical, so you can have agents where you have a parent agent that talks to a lower level agents, and you can spread it out to any number of intermediate layers, and then those agents talk on their local field bus to devices. It can be peer-to-peer, so I have two adjacent microgrids and we want to do multi-microgrid restoration. They could communicate peer-to-peer rather than up through a parent agent, or they could also be fully decentralized. And we just need to do a local control of devices on our sub-chunk of the electrical grid, and we just need a local device controller that's doing its local data aggregation, solving some sort of decentralized optimization problem. And having a distributed architecture that provides the means for us to exchange data and provide context to that is very important. With a forward-looking perspective, we can then also layer that on graph models, graph databases of the network, and then start putting those individual data compartments in a very structured way. And so we say, okay, this microgrid is a type of subscheduling area. This little low voltage network is a type of subscheduling area. It has its own applications. It's got its own local copy of its network model. The microgrid controller needs to know the topology and devices within its own microgrid, but it doesn't need to know the microgrid on the next feeder or other stuff within the feeder except for the boundary interface. So we take that compartmentalization of data, measurements, controls, and we can apply it out in a broad thinking covering both slow, high volume data exchanges like model management, optimization, design, market settlement, and high-speed applications for device controls, measurement integration, and split those out between an IT data bus for the slow high volume data and a field operations technology control bus for the high-speed measurement data. That's a whole lot of theory. What does that actually look like in practice? How is this relevant to the real world? And that is something that we are on PNNL, Oak Ridge, University of Vermont, group of us working with a group of utilities in Vermont to show how you actually put this out and make it work. First of all, why Vermont? Well, surprisingly, Vermont is actually part of the forefront of electric grid transformation. You wouldn't think Vermont as a high renewables location, but through state policies, incentives, and the right economic landscape, Vermont is approaching 45% PV penetration on their system. The transmission operator has an all-time peak load of about 1,100 megawatts across the state and going on nearly 500 megawatts of DER. This is all distribution connected rooftop solar and distribution connected solar farms. There's one transmission utility, which has a very interesting ownership structure where the transmission operator, the TOP, TSO, is owned by the distribution providers. And so that gives us a very interesting ownership landscape to be able to start deploying and showing some of these data integration concepts. The first project that we have, being Vermont, maple syrup is a big thing. They love maple trees, all of that. So we have 3 projects ongoing between us, Oak Ridge, and the utilities there, Maple Leaf, Maple Branch, Maple Root. So the first one is looking at under-frequency load shedding. The electric grid must keep a precise balance between generation and load, and that balance is indicated by grid frequency. If the frequency drops too low, we have a system in place that will automatically open feeder breakers across the system to drop distribution load and bring frequency back up. And the way I like to explain it to utility stakeholders and these types of people, it's like a ship. If the ship is properly loaded, everything's going great. It stays at 60 hertz. If the ship suddenly starts sinking, we need to make the ship lighter, throw cargo overboard. That's the equivalent of shedding load. And now the ship will become lighter and rise back up to the correct water line. With increasing amounts of distribution-connected solar and DERs, we are now seeing a case where the system as designed may not function correctly. The current regulatory requirements say utilities will go through, take their single-hour peak load, and then do all of their protection studies based on that. Problem is, due to high PV penetration, their peak load now occurs in the evening after sunset. And so they go through, do their single-hour peak load calculation. But during the daytime, those distribution feeders that were selected for UFLS may actually be backfeeding the transmission system. And so at high noon, on a warm, pleasant day, instead of an under-frequency load shedding system, we may have an under-frequency generation shedding system, and we're actually going to make our frequency problems worse. And so that is the problem that we have set out to solve with that distributed architecture. The second is improving power factor. All of those DERs are injecting power at unity power factor, and that is causing all sorts of voltage control and power factor problems at the transmission distribution interface. And of course, gonna go back, beer and foam, it's the classic volt-var analogy, but it works. We need to keep an ideal balance of beer to foam to keep our voltages stable. And these DERs are only providing beer to the system and not providing any foam. And so if we provide volt-var curves, we can solve that problem without the utility having to go out and buy more capacitor banks, install more controls, and spend utility capital as opposed to just changing the control settings on a solar farm. For the case study, we're looking at a group of islands. In this case, we don't mean electrical islands. We mean actually it's sitting in the middle of a lake. So it makes a great case study where we have very clear boundaries. It's a small real-world test case. And we see horrendous power factor at the transmission distribution interface. Ideally, you want your power factor in the 0.95, at worst 0.9, and we're seeing the power factor drop to 0.7 or even at certain times to 0 across the 2 groups of feeders that we have been studying. And at the same time, the reactive power imbalance inside the distribution feeder is driving up nodal voltages as high as 1.08, 1.09 per unit, which is going to be realistically causing problems for distribution customers. So to solve this problem, both of these are transmission distribution coordination problems. The problem is occurring at the interface where the two ends of the modeling world meet. You have the transmission model looking at transmission level SCADA, PSSE, node breaker models and their EMS. We have the distribution world looking at meter data, unbalanced power flow, and then where the two meet is where we're seeing the issue and also the big challenges in exchanging data. To solve that, we set up a time series data exchange platform in the cloud. And multi-cloud, multi-vendor, multi-platform information exchange between the transmission and distribution utilities, where the transmission utility, they have their on-premise SCADA, PyHistorian, they're pushing data up to Azure. The distribution utility is pushing their AMI data to Google Cloud. We have an intermediate AWS proxy that's pulling that data down, aggregating it on individual field message buses, and then creating that single source of truth data stream so that we can do cutting-edge T&D applications and limited field demonstrations. How does that actually work? What do we mean by aggregating data on a field message bus? Well, for this study, looking at 32 distribution substations, 70 feeders that are eligible for under-frequency load shedding. We pull them down, pull that data down onto 28 Raspberry Pi 5s running the VOLTTRON platform. VOLTTRON is a lightweight message bus and data integration platform. Originally, it was developed for the grid, but then the buildings people took off and did a lot of stuff in transactive energy and building controls with it. And then from those individual field message buses, we send it up to the central enterprise message bus located in a GridAPPS-D platform in Azure. Similar thing for solving the volt-var problems, bringing in distribution SCADA, distribution AMI data, pole top measurement data, mapping those data points to the correct places within the SIM distribution feeder model. And now we can run co-simulations. We can have the mapping of those distribution feeders to the transmission system. We can study the issues at that transmission distribution interface and how implementing volt-var curves on those solar farms will solve the issues that we see. There's a lot of work that actually goes into making that happen. It's not, these diagrams are extremely simplistic. The original one showing like, oh, data just magically moves. No, there's a lot of data mapping that happens, combining your PSSE, your protection system models, your AMI, your GIS. But SIM provides that single source of truth where we can combine all of these data sets and then start creating the copies. Okay, you're a substation controller doing under frequency load shedding for your one substation. You only need your one substation model, your feeders, your DER. And so with SIM, we can do that compartmentalization of data. Same thing for designing volt-var curves. We can take the disparate GIS, metering, pole top data, historian data, planning models, combine them all, do very accurate model validation to make sure that the simulation matches what we see in SCADA, and then develop volt-var curves. But the first use case here is how actually the mapping of message buses to topology works. So you have your centralized GridAPPS-D platform where you host the central coordination agent and then individual substation level message buses for each substation. And then if you want to go down and start doing distribution co-simulation, you then have a feeder message bus for each distribution feeder. Tie that all together, populate it with the utility data security protections, avoiding the NERC-CIP boundary, and now you have a robust modeling environment into which you can build these advanced applications. I'm not going to go into the detail of any of these applications, but if you're interested, I can put you in touch with the members of the project team who are developing these advanced algorithms for UFLS or for design of volt-var optimization, volt-var curves, how you do this co-simulation with GridAPPS-D, OpenDSS, develop robust algorithms. But most importantly, this is not a paper study. This is something that it's applied research where we are going to show the ability to send DNP3 control messages to a Schweitzer SEL351 relay at one of the Velcro substations. We're not going to do it for a relay that's actually hooked up to the real breaker. We're going to have one on a test cart, but within the same data environment, and showing that we can do that communication. And then for the volt-var curves, the solar farm owners on the feeders that we have studied, they're actually going out right now and reprogramming those inverters with the IEEE 1547 curves, and then we're going to be able to look at the SCADA and historian data and see, oh, here was the sunny day before they implemented volt-var curves. Here is an equivalent day after they implemented volt-var curves, and look at the differences between those two to show the effectiveness of that approach. Of course, this cannot happen in a vacuum. We have a very large team on the PNNL side who are working on this and making the individual components of the software, the applications, the databases, the protocol, and everything work together. And that wraps me up, and I'm happy to take questions both via chat and on from the room.
Yeah, thank you very much, Alex. One thing about being a moderator is I get to ask the first question. That's the one upside of taking the time to do it. But anyway, I would love to hear you talk. But I do want to just a quick question to start off is on this common information model, how quickly or how widely is it being adopted by industry, both on the utility side and on the vendor side? Are you seeing that how fast that being adopted from what you can see?
It is being in the transmission sector. All of the large transmission operators in the US use it at least for data exchange. They will have a SIM export available, and the transmission vendors will support a SIM import. They don't use it across the board yet as the single source of truth. ERCOT was the original pilot. They really were the ones who saw the need for the single source of truth and had the first biggest problems around data management. And so E and all of the European utilities, both Europe and China, have actually driven SIM top down. And they because they have that different regulatory structure than we do in the US, they were able to mandate it to all the utilities and then also put it into their software requisitions. Like, if you want to bid on a contract that we're offering, you must support SIM. And so that has driven the vendor community. In the distribution space, we're catching up. Distribution systems did not have that same type of data problem until the last 5 years ago. And now that the data problem from DERs, grid edge devices, is beginning to hit them, they are beginning to look at distribution network model management systems based on SIM. And at this point, it's just the big IOUs at this point, Ameren, SoCal Edison, these types of people who are getting interested and seeing that based on the size of their data problems, they need to move to a common standard.
I know that we've been hearing from at least one large vendor asking us to help them with their SIM conversion process, because obviously they want to get their tools into a SIM format. So I think that's very exciting. Okay, let's start with the room. Any questions from the room? Please note that that room is on mute. So if there's any questions from the room, please take it off and just shout it out. Nothing right away? Okay, we'll go to our online participants. Any questions from those of you online? Not seeing anything. Well, actually, we do have a few more minutes if there's anything else that you want to add. Anything that you want to make sure you get across?
Just oh.
Well, put it this way. As for those in the room who are students or grad students and maybe some undergrads in there, how can they get experience with that SIM model and what they're doing, do you think?
Yeah, absolutely. That's exactly where I was thinking to go. So as a grad student, there is a certain heavier lift to adopting a standards-based approach for your research. But then once you have done that, it pays off. So yes, you can go and hand build your own custom PSSE or PowerWorld or OpenDSS model, and it works for the first time you need to do it. But then once you need to go to another model, say you built your application on the 123 bus, and now you want to go to a different model. If you don't have a common data format like SIM, you're going to need to go through and redo all of your application code, all of your optimization parameters, anywhere where you had hard-coded information about that model, you'll have to go through and redo it. If you want to start benchmarking your algorithm against multiple models, multiple types of data, then this is where adopting something like SIM really comes in, because you only have to write your application once. And you say, I'm going to do a high-level call for all types of power transformer objects. Well, then, since you've built it against the key of power transformer, whether it's the 13 node, the 123 node, the 8500 node, Texas A&M synthetic models, they're all still the same power transformer object, and your code will run with just minor tweaks. It also gives you great experience in working with standards-based platforms and more advanced data environments, which is something that the utility industry is keen to move towards.
I think that's really great advice. I just wish we had this back when I was a power systems engineer. Remember our utility, like for example, our topology models for our power flow didn't even match that we're using for our short circuit models. So they didn't, even within the same company, within the same engineering department, our models didn't match. So that really is a really important thing to keep in mind. Okay, let's go around one more time. Any other questions from the room?
Can you hear me?
Yes, loud and clear.
Yeah, awesome. Alex, first of all, I just want to thank you for the excellent presentation. Yeah, it was like very, I would say, airtight. That's why I can't even I would say form much of a question. I would just ask that. So what I fundamentally understood is that ultimately you do need some sort of interfacing exchange, let's say from transmission to distribution, or at any level, to communicate between two different systems which might have fundamentally different things. You do need some sort of to build some sort of interfacing mechanism. And you said that with SIM model, at least there is a certainty in how you can you have a certainty in what language should be used, and the terminology is like easier to exchange. Still, like fundamentally, like what I understood is like this is all like basically like a very large software engineering problem. And my question is that since basically there are n number of different kinds of systems, and my question is because every system can have completely different components, different kinds of messages, different contingencies, which no one person I believe can ever know. So does it involve, let's say, someone like you or some specific people to like sit down and like analyze the entire system and get a rough idea of, okay, what kind of information should be exchanged? Or is it more of a, as you said, like as part of the distributed architecture, as long as two parties which are connected to each other, they agree on the terms and the information to be exchanged, that works, and a smart engineer can just design a good interface between the two things?
I'll actually say both. So you need a system architect, system integrator who knows who are the right people to get into the room so that they can have that second conversation that you were talking about, the peer-to-peer. But you do need, I'm actually going to start pulling in optimization terms. You need a coordination agent, a hierarchical agent, so that the two can be communicating correctly and can also serve as a technical translator. Because if you take a transmission person and a distribution person, they're even going to use the word bus to mean different things. It could be a physical bus bar. It could be a three-phase mathematical topology bus from PSSE. A distribution person is going to use the word node instead, and bus means the combination of your individual A, B, and C phases. And so you need a technical translator to do that coordination so that then step out, and then you can have peer-to-peer once you have agreed on between the individual lower level agents what information is going to be exchanged, how is it going to be exchanged, what frequency, what communications protocol. There's a lot of peer-to-peer agreement that needs to happen, but you do need a top-level architect to facilitate that.
But one thing I would hope over time, as the common information model gets adopted by both the user community and the vendor community, that the amount of translation starts to go away, right? That models are built from the ground up with that kind of basic, so that the interpretation model gets less important. So hopefully over time, there's less need for that kind of coordination, I would hope.
Absolutely. And it's also a case of, in the software business, we sometimes call a recipe, where it covers 80%, 90% of your use case, and then you can just tweak little things to make it work for your own individual needs. If you're doing it without a standard, you have to build that every single time. If you have a common model, you can then look over at your utility neighbors and say like, oh, this utility like Ameren or ERCOT or National Grid in the UK, they've implemented SIM. And they're willing to talk to us about how they did it, what were their lessons learned, how can we use the same vendors, the same interfaces to repeat that success. And on the PNNL side, that's actually the entire reason why we're doing this, is because we don't want this to be a one-off study. We want other utilities to be able to come in, look at our architecture diagrams, look at the communications messages, look at the algorithms, and say, oh yeah, we can copy this. We can take this back to our preferred vendors, which may be entirely different, and our databases, which are different, but we can copy this recipe and follow it.
Well, what we've certainly found with our partners is that if you have a champion within our partner, like our at Velco, it makes it much easier to get adoption. I know there's many utilities that don't have that. So if nothing else, for those of you who are at WSU, if you go out into the real world, carry this message with you, because that's what we need. We need champions throughout the industry. Again, I keep always saying it has to be both on the user side, the utility side, and on the vendor side. It can't be done. They have to happen together. So I would encourage you to look at the benefits of having this kind of structure as you go out in the industry. All right. Coming up at the top of the hour, so I'll go around again. Anything else from the room? Great question, by the way. Thank you for your participation. And from else online?
For explaining.
I'm sorry.
Yeah. Thank you for explaining, Chris and Alex. Yep.
Yep. Okay, well, we'll call it a day. Thank you very much, Alex. Great presentation as always, and thank you for people in the room and people online. Appreciate your participation, and I think you have our contact information. If there's any other questions that come up later, we'll be happy to respond. So thank you, and have a great day.